Okay. Okay. Now, lastly, the morning sessions we already look at uh, what solutions that might happen, okay, in the boundary value problem. Then we may have some general conditions that can make up to the solutions. Okay. Now, let me give you more idea on that the boundary value problem. It can have many solutions, one solution, or no solution. Okay. Okay, let's say we are having the x double prime plus 16x plus 0. Let's say this is our differential equation. Okay. So this is a second order differential equations, and let me just give you the the parameter t solutions for this dE. Okay, the solution is x equal c1 cosine 4t plus c2 sine 4t, and you can check the confirmations. You can differentiate twice and try to make out the dE, whether it's make up to 0 or not. I think based on what we have before, we can verify, and this is the solution is true. But what we are going to do with the solution is we are going to observe what kind of solutions when we have different cases. Okay. Okay. So for first conditions, suppose that we have boundary. Let me write boundary conditions. BC is boundary condition. Let me write in green. BC is 0, 0, and at pi over 2 is also 0. Okay, now observe the first conditions. So when 0, 0, this is 0, c1 cosine 0 plus c2 sine 0. This is becomes 0. This is becomes c1 becomes 0. Okay, and then this implies that x is c2 sine 40. Okay? But when it's pi over 2, 0, zero equal c2 sine 2 pi. Okay. So for any c2, since sine 2 pi is 0, so we can have any choice for c2. So the boundary problem, so the boundary, the DVP has infinitely many solutions, especially for this case here. Since we know that the sine 2 pi is 0, so the c2 can be any numbers, right? Okay. So we call that this is having infinitely many solutions. And we may see what kind of graph from here. Just give you this graph that if we change the C2 from 1/2 they are all having the same behavior, which is they are starting from here, the cross section with the xt axis here and here. Okay, and the difference is just the amplitude here. Right? Okay. Even when you are making the C2 is negative, it can also be a solution because they are having this 0, pi/2, okay, 0, and then pi/2 here. They are always having the crossing the t-axis. Okay. So it's infinitely many solutions. So that's the first case. Second case. If we suppose we change the boundary condition. So BPP x double prime and then let's say we have x pi/8. Okay. Now we change the second one here. We change. Of course, from the first one, from the first value here, the boundary value here, still requires that C1 still need to be 0. Okay. But for x pi/8, this requires to be C2 sine 4t. And if we let the x 0 as the conditions here, this is pi/8. Pi/8 becomes pi/2, right? So we are having it's exactly at C2 will be a 0. Okay. So x equals 0 is a solution of this BPP. Okay. I hope you don't get confused. Usually we are having y. This is a function of a t. Okay? So we are using x exchanging to y, but actually it's the same way when we have the differential equations as the previous examples. Okay. So this is the solution for this boundary value problem, and we can also prove that x equals 0 is the only solution. Is the only solution. Okay, that's the second case. So it's fit when it define the C2 itself, right? Okay, now the third conditions, we change the problem, and we change the problem. So BPP okay, of course from the first one we get that C1 is 0. So from get that C1 is 0, and then from the second one, we apply this. Okay, if we apply, it will lead to C2 sine 40. Let me write 40. So it's apply. So it has a contradiction that this has, it's supposed to be 1 C2 sine. Now we have pi over 2, right? Pi over 2 multiplied by 4 is supposed to be 2 pi, right? Now sine 2 pi is supposed to be 0, right? Sine 2 pi is supposed to be 0. But if this is 0, but we have a condition that we take as our boundary that x is equal 1, right? So it seems it's has contradictions, right? It seems contradict. Okay. Now, when we see these contradictions in some boundary value, we can say that within this BPP, that this BPP has no solution. Okay. So first, it can be many solutions. So you can have a family of solutions that you can fit within your boundary value problem. The second one, you only have exact one solution. Okay. And the last one, when you have a solutions and check and you confirm, you see some contradiction, okay, within the boundary and the solution. Then you cannot use that as your solution. So no solution for that case. Okay. Okay, that's the idea on how we can think a boundary value problem. Okay, and when we have at least we need to check. Okay, we check the value and check the solution. Okay, whether it's contradict or it has many solutions. Okay, if not, then it's just one exact solution. Okay, let me give you another homogeneous notes, okay, on higher order. So homogeneous equation. Okay. Okay, we call this homogeneous. And if you have another expression on the right side, we call this non-homogeneous. Okay, we need to make some definitions, not definition, but some restrictions. Okay, so coefficients a for any nth x for this coefficient, starting from 0, 1 until some n. The coefficients, they are continuous. And right hand side, g of x also continues. And x is not equal 0 for every x in interval. Okay, so why we need to have these two, homogeneous and non-homogeneous? So if we want to solve non-homogeneous linear equation, we also need to be able to solve the homogeneous one first. Okay, we will see later what I mean by that. Okay. Okay. Okay, homogeneous. Okay, let me give you another few. Okay. Some operators in differential equations. Um, Actually, what we have and what we learn is on basis similar what in which we have in calculus. Okay, if you remember. So let me give you just some notes. Okay, there are some differential operators that you are going to find out. Okay, if we have dy dx, we call this is a derivative, right? We can also call this with the differential operators that we call d. Okay, and sometimes we can make up this means dy, or this is what this means is d dx and then d, like that. Or if we have a function of x, so if y is function of x, so this will be y. That means the ddx is our d, so we can write d and or writing d like that and y. Okay, to give you the new symbols that probably we are going to see a lot. Okay, so if we have d and then we have cos 4x, which means that it's it's going to be the same as when we have d dx and cos 4x. So this is actually equivalent, okay? Right? In a natural way, if you have some order of some higher order n, like for example n, we are going to take it into our operators. This means that the d like that, having some n and our function. So we can express the polynomial using the d. Okay? So for example, if we have d plus 3, or let me write 5x cubed d cubed minus 6x squared d squared plus 4x d plus 9, this is also a differential operator. Okay. Or let me just define in a more general way. We define the nth order of differential operator. So let's say L, okay, is an x dn plus or maybe let me give you notes here that if we have d dx and then dy dx, this is usually we write the second derivative, right? We can also write in terms of d, okay? So this is dy. To make it clear that this is right, wrong should be having the same height. Okay, okay, and then we have a definitions for some nth order differential operator. Okay, now we may have a basic property for the differentiation. So if we have the differential operators, we have a function that is having a constant c and a function of x like that. This is equal to, we can move out the constant d and f of x. Okay, not really a problem, so it's a constant. Or another property that has I think important characteristic, if we have plus two functions that we may multiply each one. And it means that this L is also a differential operator. So the differential operators differential operator L, it possesses what we call the linearity property. Property. Okay. So L operating on a linear combination of two differentiable functions. So the L is the same as linear combination of L operating on individual function. In symbols, this means that L, if we say we have a constant alpha beta, and we have a differentiable function f and g, we may take this out. Sorry, g, sorry. Where the alpha and beta are constants. So we say that this L is a linear operator. Okay, now how do we apply this? Okay, how do you apply? So if we have y double prime plus 5y prime plus 6y equal 5x minus 3. Okay, now we can write this in terms of differential operators. D or we may write now we can write this using the linear operator and writing this and this for homogeneous and non-homogeneous. Okay. Or maybe to make it understandable for what this L means. Okay. Let me write. Let me just copy from here. Okay. Okay, so what does it mean is this L it can write the uh, all the combinations that has D inside or the differential equation and make it more simple. So just write L and then L y equals 0 means the homogeneous one and L y gx is the non-homogeneous one. We can also see from here also that L is an operator that involves inside having the D and the constant. Okay, the D is course, the differential, okay, the operator. Okay. Okay. I think we can look more into what we call the superposition. Okay. So the previous one is just an intro on what we are going to see in more cases. So the first theorem in higher order is the superpositions. Superposition principle. Okay, let's say we have the homogeneous equations we are going to observe. Okay. First is we are going to see some solutions. Okay, let's say y1, y2, yk. They are the solutions of homogeneous nth order dE on interval I. Then a linear combination L, or let me write directly in terms of y. This will be C1 y1 x plus, or let me write this with y, plus C2 where the Ci equal have I start from 0, 1, I think start from 1. Start from 1, 2, until k. They are all arbitrary constant. Arbitrary constants, and they are also the solutions on interval I. Okay. So to give you some understanding, let's say we have some illustration. Okay, let me give you y double prime plus, let's say px y prime plus qx y, let's say equals 0 because it's homogeneous. Now suppose y1 and y2 solve the given dE. Okay, let's say this is our solution, y1 and y2. Then what the superpositions gives summarize, okay, give you summarize that if you know that y1 and y2 is the solution, then the total solution, or the general solution, is you will have a c1 y1 plus c2 y2, and we can say that this also solves the differential equation here. Okay, let's say we try to differentiate the solutions. Okay, let's say we are going to have y prime. Okay, this will be going to have y prime, or let me just give you directly. Let's substitute. Okay, let's substitute these solutions to our differential equation directly. Okay, so proving that c1 y1 plus c2 y2 double prime, it means that we are going to differentiate twice and then plus P of x, and then y prime, c1 y1 plus c2 y2, differentiate once, okay, and then plus q, and then c1 y1 plus c2 y2, okay, right. Now this as the linear operator, as we did in L and D before, then we can take this, or we can write in terms of L, Y, okay, and then we can also write like this. But let me just write C1 Y1 double prime, and then plus C2 Y2 double prime, and plus P. Let me just write Px as just P, and then C1 Y1 prime plus C2 Y2 prime. Okay, and that's plus Q C1 Y1 plus C2 Y2. Okay. Now we can have C1, 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 and Y1. Okay, C1, Y1 we can combine together. So C1, this is Y1 double prime plus, okay, plus P Y1 prime plus Q Y1, okay, and then plus C2, this will be Y2 double prime, and then P Y2 prime, and then plus Q Y2. Okay, now what is this? This is our homogeneous equation, right? It's equal 0. So this is becomes equal 0. This is become equal 0, and therefore the whole thing here will become 0. Okay, so that means that the solution can be proven to be correct. So this C1 Y1 plus C2 Y2 is true that it's true, or maybe is can be solved, can solve the differential equation. Okay. Okay. Wait. Homogeneous. Okay. So as a conclusion, a constant multiple y c1 y1 x of solution y1x of homogeneous linear differential equation is also a solution. And then homogeneous linear differential equation, okay, always possess trivial solution in which y is 0. Okay, that's the conclusion, the superposition. Okay. Okay. Okay, any questions first? Okay. So the superposition is telling you that if you have two solutions, y1 and y2, that can solve, which means that you will also have the solutions that contain y1 and y2. Okay. Okay. Okay, let me give you a more practical example of what the superpositions mean. Okay. Okay. Let me give you. Let's say we have y1 is x squared, y2 is x squared ln x. Let's say the y1 and y2 are solutions of homogeneous linear differential equation. Let's say we have x cubed y triple prime minus 2x y prime plus 4y equals 0. And we have interval 0, infinity. Now, because we know that this has these solutions, then by superposition, theorem, then y c1, let me write it, c1 x squared plus c2 x squared ln x, also a solution. Okay, that's what it means, right, for the superpositions. Okay, now the important context and important important things aside from the superposition is the linear dependency. Okay, linear dependency. We call linear dependence. Okay, a set of function. Okay, a set of function is we call linearly dependent on some interval if exists constant c1, c2, cn exists constant c1, c2 until cn, not all 0, such that c1 f1 of x plus c2 f2 of x plus 0. for every x in interval, if the set of functions is not, okay, so this is the second statement. So if it's not linearly dependent, then we call linearly independent. Perhaps it's like too many technical words, but what it means is you can have some connection between y1 and y2, whether it has dependency or not. Okay? So we call y1 and y2, we call linearly dependent if, this is my simple definition, if you want to maybe understand it more practically, if they are not a scalar multiple of each other. This is the very simple definition that I can have. Okay? For example, x squared, right. For example, x squared and then 3x squared. Okay. This is linear dependent. Okay, because you know that the one function is multiplied by scalar and becomes another function. Okay. But if you have sine, for example, sine x and cosine x, they are not dependent. Okay, so we call this the second one linear independent. Okay. I hope this is very clear. Okay, it's clear. Okay, I hope it's clear. So you can multiply with a constant and it becomes another function, and we call that those two functions are linearly dependent. Okay, I think quite clear. Okay, from those definitions. Okay. But if you have, for example, if you have uh, mm, let's say this is sine 2x, and the other one is sine x cos x. They are linear dependent, okay? Linear dependent. So I just need to make you think, okay? Because sine 2x, you can have 2 sine x cos x, right? And it becomes twice as the other function, which is we have differences in a constant, right? In the scalar. That's why it's a linear dependent. Okay. Okay. Uh, okay, we can move to other section. But let me just give you this and maybe take a break for 5 minutes. Okay, 5 minute breaks. Okay. Okay. Let's continue. Okay. Now, of course, the important point in differential equation is how to find the solutions, right? How to symbolize the solutions if it's having curve, right? So solutions to the differential equations. Okay. So we have distinguished the linear dependent and linear independent. Okay. Now we are more interested in linear independent function. Independent functions or solution in this case of differential equation. Okay. We can we can settle we can we can use determinant and we can write down some settlement. So suppose um, each of functions f1x, f2x until fn x, they possess at least n minus 1 derivatives. So what that means? It means that all these functions, okay, they have at least they can be derived. Okay, they can be derived. Okay. So we call the determinant. We call the Wronskian determinant Wronskian, where we usually write as W, and then F1, F2 until Fn. This is F1, F2, Fn, and then F1 prime, F2 prime, Fn prime. So we can set up a determinant that is consists of a function, its derivative, its second derivative until some nth derivative. Okay, so we can set up this determinant. So the prime here denotes derivative. So we call this Wronskian of the function. Okay, let me write the nodes and how to use this Wronskian. So let y1, y2, y3 until yn. All of this, let me write. Let y1, y2 until yn be n solutions of homogeneous linear or some nth order of differential equation on interval I. Okay, let me just write I in interval. Then, okay, then set of solution is linearly independent on the interval I, okay, if and only if the Wronskian is not equal to 0, okay, for every x in the interval. Okay. So we need to show that the Wronskian, the determinant, is not equal to 0. So we can call that it's linearly dependent. Okay. So we haven't yet find the method how to find exactly what kind of solution that we have. We are just looking some solutions and see whether what kind of restrictions does these solutions have. Okay. So first, we tell the homogeneous, non-homogeneous, right? And then we have the linear dependency, whether it's dependent or independent, and we are more interested in linear independence, okay? And to find out whether it has set of solutions is through the Wronskian function or Wronskian solution. Now, to use this Wronskian, okay, let me just give you a brief Wronskian, how to use this Wronskian. Okay, example, if y1x and y2x are solutions of differential equations, x squared y double prime plus 2 y double prime plus 7 x y prime plus 13 y. Okay, let's say we just have this as our solutions, and if we want to check using the Wronskian, notice that then we need to find y1 prime, y2 prime, etc., right? So, well, what suggestions that we are going to have here is this is interval solution. I forgot to write. It's from 0 to infinity. So notice that from here, from this differential equation, the coefficients. So first we need to separate. Okay, so the y double prime is and y prime and y. This is our variable that we need to be observed. Okay, and the other part is the coefficient. Okay, so we can write down that a2x is x squared, a1x is 7x, and a0x is 13. Okay. Okay. And also a2x is not equal 0 for x in interval I, right? So the Wronskian y1x y2x. Remember the Wronskian? It's going to be, it's start with the first one, the second one, and the second one here is the derivatives, and then more derivatives to come. So if we have like more than you can, if you have more than if you have more than two solutions, it goes to the right, and if you have more than the highest order, you go to the bottom, right? And now we have the y1 is, let me just write first, okay, and see whether it's easy or not to solve this. And of course, the second row is supposed to be the derivative, right? But let me just write the derivative, and you can just use calculator to check whether it's correct or no. This is just an illustration on how messy it can be in the Wronskian if you are not careful. So we are having the quotient rule, right? So this will be negative 2x squared sine minus 3x squared. And this will be 2x squared cos 2x x to the power of 6, and we are going to have calculation for determinant. Okay? And determinant means that this multiply minus this multiply, right? But can we multiply this? And it seems really messy, right? Rather than directly use this determinant, we can choose, okay, we can choose x equal 1 on interval of, okay, because we have this interval 0 to infinity. So we can just take some example for x equal 1. And we can find the Wronskian directly at x equal 1. So it's easy to be compute and easy to be analyzed. So this becomes cos 0 is 1, right? 1 sine 0, right? And then this will be, you can just plug in x equal 1. So this will be negative 3, and this will be 2. So every sine will be 0, every cos will be just 1, right? So it's correct. And if we try to calculate this, it will be 2. Okay, so it's not equal 0, right? And sufficient that the conclusion from this Wronskian just to say that our y1x and y2x are linearly independent. Independent on interval 0 to infinity. Yeah, just using just one example of x, it's sufficient to conclude the solution, to conclude that it's linearly independent. Okay, now the theorem why we need the linearly independent solutions. Okay? So any set of y1, y2 until yn of n linearly independent solutions of homogeneous linear nth order differential equation on some interval I is said to be a fundamental fun, 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 fundamental set of solutions on interval I. Okay, so this is why we need to know whether the equation is linear dependent, the solution is linearly dependent or linearly independent. Okay. Okay. Okay, this is the fundamental set of solutions. Okay, the next theorem is the existence. Okay, the existence. So there exists fundamental set of solutions for homogeneous linear and nth order differential equation on interval I. So if you have, so first we need to define whether it's homogeneous or not. Okay. So for every homogeneous linear DE, there will always fundamental set of solution. Okay, I think that's simple. And because we already know the linear independence, the fundamental set of solution, then we can write down the general solutions for homogeneous equations. Okay, let y1, y2 until yn be a fundamental set of solutions of homogeneous linear and order differential equations on interval I. Then general solution of the equation on interval I is y c1 y1 x plus c2 y2 x plus until plus cn yn x. Okay, that is the general solutions where the c is an arbitrary constant. So c is arbitrary constant. I think the proof not really important to know. Okay, I can skip the proving. So in the future, for some questions in the higher order, sometimes we need to assume some of the solutions, and we need to verify whether our assumption is true. Okay. That is sometimes what we are going to do in the future. Okay, like for example, let me just give you a slightly simple equations. Let's say we have differential equations, that is this equations. Let's say we already have our solution, that is y1 and y2. They both known for the solutions for homogeneous DE on all interval, on all x. Okay. So if we inspect the solutions, so if we check this, okay, if you want, we are going to check using the Wronskian. So Wronskian, how to use the Wronskian is basically write down the solutions here, y1, y2, it's just only have two solutions here, and then the next part is writing the derivatives. So 3 3e to the power of 3x negative 3e negative 3x. Okay. And then we try to build or to construct the determinant, and by adding, multiply and adding, so multiply and minus, subtract, and then minus 3, right? So it's minus 6. Of course, this is not equal 0, so we know that this is linearly independent. So e with power 3x and e with power of negative 3x are linearly independent. And we conclude that y1 and y2 are or form a fundamental set of solutions. And as implications, we have y equal c1 e 3x plus c2 e negative 3x this becomes the general solution. Is general solution of equations on interval. Okay.
Professor, is this because of superposition?
Hmm?
Is this because of the superposition or no? Like this solution.
Yeah. So if we know that we have a y1, yeah, it came from the base. The basic is came from the superpositions. Okay, but we also need to check the from Wronskian. So if we check the determinant, if we have not, if the result is not equal 0, then our solution is linearly independent, and that is what we are looking for. Okay, what we are looking for. So if they are both linearly independent, we can say that we can combine these two solutions into one general solution because of the superposition, and because of the superposition, and we call that this solution as a general solution. Okay, this is just to telling you how to write solutions in the higher order differential equation, because we haven't yet learned some technical or some method to find out the solution. What are the method, right? But we are just looking at what can we construct as a solution. Okay? So from the first example and this example, I just saying that okay, let's say this is the solutions, and how do we prove it is linearly independent, and how we can see that if this is fundamental set of solutions, then we can combine both solutions with a superposition and make a general solution.
Okay, thank you, Professor.
Okay. And the Wronskian, it can be as many as the order is. Okay, so for example, we have this is 2 by 2, right? Because we have only two solutions, right? Only two solutions. If you have like three solutions, like for example, in the third order, then we need to have 3 by 3, 3 columns, 3 row. Okay. Okay, like for example, if we add more, like for example, we add y1 is e to the x, y2 is e with 2x, y3 is e 3x, like this, and we have so this is solutions of the higher order, the third order equations, y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. Okay, now this is a third order, right? Third order equation. So if we want to check whether all the solutions here are linearly independent, then we might write in terms of Wronskian. And we need to differentiate at least twice, right? And of course, you need to be able to you need to review some of concept in mathematics. For example, finding this determinant 3 by 3. I think you can review that on the matrix. Okay, we have also matrix later on, but I will just focus on some parts in matrix, because I believe you're already familiar with matrix. Okay, so I don't really want to repeat the basic concept. Okay, so I will just go and review quickly what is the method, okay, that we are going to focus on. So let's say we have here. Okay, so if you want to compute, then we can compute and finding out through so we can because let's say we are going to see this one. Okay. So we are going to have e to the x and then determinant of so 18 e 5x minus 12 e 5x and then minus 9e 5x minus 3e 4x. And then plus e3x 4e3x minus 2e3x. Yeah, I think I will leave this calculation for you, but the the total here, the determinant is 2e with power of 6x, and we know that e is positive value, it's not equal 0. So this is linearly independent, and we conclude that y c1 ex plus c2 e2x plus c3 e3x will be the general solutions. Okay. Okay, now we are going to move to non-homogeneous equations. So in this part, okay, this is still I consider like a set of introductions of the higher order differential equations that is not really telling you the method or the techniques how to find the solution, but rather we are going to have a lay ground uh, on the interval, what kind of solution that we are going to expect, and how to confirm the solutions, and uh, uh, how the solutions can be combined within the superposition principles. Okay, so this is just like a groundwork for the introduction. Okay, so after we have some sort of introduction on homogeneous, non-homogeneous, and the linear dependency. After that, we are going to move on to how to technically how to find the solution itself. So what kind of technique that we have. Okay, so I hope you understand. The very first part here for the higher order differential equation is really going to have more definitions, some technical terms. Okay, so I hope you are you understand at least what we are doing here. Okay, what we are doing here. It seems like a lot of technical words, a lot of definitions, but when we are going to apply that in the examples, okay, how to simulate, I believe there will be more. It will be more practical. Okay, it will be more practical. Okay. Okay. So non-homogeneous equations. Okay. We usually write yp, okay, We call this for a particular solution of equations that notably satisfy the non-homogeneous. Okay. So, for example, if we have y double prime plus 9y equal to 27, it's really straightforward if you say that the particle solution is just 3. Okay. So yp equal 3 is particular solution Okay. Now let me write in more general. Okay. So if y1, y2 until yk, they are all solutions. Solutions on interval. Let me write this is homogeneous to make it clear that this is particularly homogeneous solutions on interval, sum of rows on interval, and yp is particular solutions of non-homogeneous. Also on interval, on the same interval. Then we may have linear combinations, and then that combine these two, okay, combine homogeneous and non-homogeneous. So C1 y1 of x plus C2 y2 of x plus until k, and then plus a particular solution. Okay. So we can call that this solution here is also a solution of non-homogeneous equation. So this becomes the general equations or general solutions. General solutions of non-homogeneous. And of course, makes sense, okay? It makes sense. Why? Because if you remember the homogeneous equations, when you have the differential operators, let me write, okay? Let me write with green. So if we have C1 y1x plus C2 y2x, okay, and plus until ck ykx, okay, if we map this, map into 0, right, by the operator L, okay, by operator L. Okay. If you remember, this is what we did previously when we proved that the homogeneous this will be the solution for homogeneous because it will result in 0. Okay. So this whole thing here will be mapping into 0 from the differential operators. Okay. And the yp, the particular solutions, this will map into the g of x, right? Now if we are using if we use k equal n, and linearly independent solution of this dE, of the n order dE, then this expression here, of course, as I mentioned here, this is the general solutions of the non-homogeneous. So interestingly, if you want to find the non-homogeneous solutions, you need to consider the homogeneous also. Okay, so homogeneous is considered in terms of y1 until y some yn or yk, and then yp is the particular solutions for non-homogeneous one. Okay, so you have two combination here, okay, homogeneous and non-homogeneous. We can also write the general solutions in more a simple way rather than this having some elements out of uh, several constant. We can write that if we can say that yc, okay, yc linear combinations, this is c1 y1x plus c2 y2x plus until cn yn. Let me write instead of k using n to make it more general. So this is called the complementary function. So we can write y is yc of x plus yp of x. Of course, this is the homogeneous, and this one is non-homogeneous. And we can say that the solution itself is complementary plus any particular solution. So this is the general solution of non-homogeneous. Okay, now if we look on, okay, so let example, okay, let yp is negative 11 over 12 minus 1 over 2x is a particular solution of y triple prime So of course this is non-homogeneous because of this 3x, right? So we can, okay, to analyze or to construct the general solutions, what we are going to do is we are going to take this into homogeneous. So we need to make it into 0. So y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. And I think, have we done this before? Let me check example. Yeah, this is from the previous example here. Okay, the same equations. So from the homogeneous one, we know that this will be having yc equal c1e with power of x plus c2e to x plus c3e with power of 3x. Okay, this is on interval for all x's, right? Now the general solutions then yc plus yp. Okay, let's slowly, we can see that how to construct homogeneous, non-homogeneous. The last sections on the first part of introduction here is we have another superposition principle for non-homogeneous. Okay, so the idea now we have homogeneous, non-homogeneous. Okay, usually we call yp for particular solutions. That is for non-homogeneous. For homogeneous ones, usually we are just using yc or just make it homogeneous and find some constructions that has, for example, this one. This is our homogeneous. Okay? And then for the whole solutions, we are going to have the homogeneous solutions and non-homogeneous one, or the particular one. Or we could say that the non-homogeneous solutions will be include the homogeneous solutions and particular solutions. Okay, that is the non-homogeneous. Okay. Okay, let me go to another principle that related to superposition in non-homogeneous. Okay. So we have yp1, okay, yp2, ypk. Pk particular, so we have some particular solutions until k number, okay, of non-homogeneous linear and order differential equations on interval I. Now it is corresponding to k existing functions. Let's say it's a function g1, g2, up until gk. That is suppose the ypi. This is a particular solution of corresponding DE a n x y n plus okay, where I is from 1 to up until k. Then the particular solutions, now we can have a superposition in the particular solution. So yp1 x plus yp2 x plus until ypk x. Now this ypx is a particular solution. Okay. So this is particular solution of the an x this is it's exactly the same thing. It's equal g1x plus until gk of x. Okay. Okay, that's it. The layground for the introductions for higher order differential equation. Okay. Okay. Okay, before we move to next sections, the reduction of order, I would like just to give you some briefly concept. Okay, so your textbook, it's actually they are using the So all the higher order, they give the theory in the beginning, theory of linear equations, and move on to reduction of order, and then move on to homogeneous linear equation with constant coefficients. Okay. And there are of the other two undeterminate coefficients, variation of parameters. They are all I think we are going to solve. Okay. But I think not all. Some part in these chapters we will skip. Okay. But before we go to reduction of order, let me just give you a quick review. Let me check whether we are. Okay, I think we can just follow the textbook. Okay. Okay, so next section here is we call the reduction of order. Okay. Hey, suppose y of x denotes a solution of equations, let's say the second order differential equation. Let me just write the general form. Okay. Let's say we have the y of x as a solution. Now, the next step is what is the second solution? So we need to seek out or to find y2x so that y1 and y2 linearly independent. Okay. So the ratio, because they are not in the scalar multiplication, so y2 over y1 is, we say, non-constant on interval I, right? Okay, so because they are linearly independent. So we can say that y2 over y1 is a function of x, let's say u, or y2 of x is u of x multiplied with y1 x. So we are going to, it's kind of similar to substitutions. It's kind of similar. So we are going to find out this y2 or idea. Let me write here. Find u of x by sub y2 of x with u of x y1 of x into dE. Okay. So basically that's the idea. So we need to find, because we know that y1 and y2, they are not dependent, so they are linearly independent. So we will find the relation between y1 and y2 that is non-constant, or in our case here, a functions, or rather a function. Right? Okay, let me give you example cases, and then we can have a general solution and general case. So example, given that y1 is e with power of x, if this is a solution of dE, y double prime minus y equals 0 on interval, on all intervals. y2 is equal, so we need to find y2. So, solutions. So let y equal u of x multiplied with y1 of x, or simply we write u of x multiplied with e with power of x because it's e, right? So we take the derivative and take the product rule. We will have u e to the x plus u prime e to the x. Okay. And from here, we take another one and make it second derivatives. So this will be u e to the x plus u prime e to the x plus u prime e to the x plus ex u double prime. Or we can write u e x plus 2 ex u prime plus ex u double prime. Okay, the dE is y double prime minus y. So y double prime minus y equal to 0. So, let me write this is just y prime to make it easy to follow. So u ex plus 2 ex u prime plus e to the x u double prime minus so this will be cancelled. This will be cancelled with this. So we will have e to the x u prime plus u u double prime is this correct? This is u double prime, and u prime is equal to 0. Let me check here. Y prime. Oh, sorry. It's supposed to be y, so this is wrong conclusions. So u e x plus 2 ex u prime plus ex u double prime, and e is just u ex. Okay, so it's just canceling that, and we have 2u prime plus u double prime is supposed to be equal to 0 because of the given equation, right? So e to the x will never be 0, right? So the one that makes 0 is just the inside equation here. So the u double prime plus 2u prime is equal to 0. Okay, if we make another substitutions, okay, if we make substitutions, that is w is u prime, okay. If we make this y prime, and it's making another u double prime, okay, so we make a new equation that is y prime plus 2 w prime plus 2w equals 0. And remember that this becomes our linear order differential equations, right? And we can use the integrating factor that we have in previous chapter in the first order, right? So the integrating factor is using 2, so e with power of integrate 2 dx so we have e with power of 2x. So we multiply, so multiply with e to x, so we have and take the product form. I think this is the product form. Yeah, right. Okay. Then integrate with respect to x. So this will become, let me move here, e to x w is equal a constant. So w is e negative 2x, or w is u prime, so u prime equals c1 e negative 2x. Let me just write this is c1. Okay. And we integrate again with respect to the x. Then we will have u is negative half c1 e negative 2x plus another constant. Okay. Now we have y is ux ex, right? So this will be negative c1 over 2 e negative 2 multiply with x become x negative x plus c2 multiply with e to the x. Okay. And then we need to choose the c2 and c1 and c2 and c1s. Okay, so choosing c1 equal negative 2 and c2 equals 0. Let me write so from here we find the second solutions, that is y2 is e to negative x. And then we can check with the Wronskian ex e with power of negative x, that is it's supposed to be not equal to 0, but you can check anyway using the determinant. So the conclusion here that this second solution is true, that is our desired solution, that is linearly independent. So y1 is e to the x, y2 is e to the negative x. And actually the general expression or general solution of y double prime minus y is y, if you remember what we write here, oh, this is not x, sorry, 2. So this is general solutions. With some certain solutions, with some certain constant, we get y1 and y2. Because you see that the y1 and y2 is here, right? This is y2, this is y1. So that's why we call the general solution, because it's containing these two solutions. Okay, this is using some example, but let me just write in more general case. Okay, what kind of restriction or notation that we need to write. So, of course, by this higher differential equations, we are able to see that from the chapter 1, the introductions, the first order, and then it seems that in higher order, what I feel is really jump out, right? It's really jumping out. So if you are not able to keep up the first differential equations, to understand most of the part in the higher DE, it will be very difficult, because some of the method we are going to borrow from the first order, like the separable, the substitutions, the linear order, the linear first order, the integrating factor. They are all will be also, we can consider to use that also, okay? Because there is no general method, okay, in the second order or the higher order. Okay. And what we can actually analyze in the higher order is we are going to have some method that is actually involving some guessing, and then we check one by one whether it's true or not. We will see that as well. Okay. Okay. So let me go through the general case. Okay, how to find the second solution. Okay, suppose the standard form, let me write the standard form, is y double prime plus p of x, or let me write pq is, I think, better, this one. P of x and q of x, let's say it's both are continuous on some interval I. Okay. And let's say we have y1x is a known solution on the interval I, and y1x also not equal 0 for every x in the interval I. Okay. If we define that y is having ux y1x, okay, it follows that if we have a product rule, this will be u y1 prime plus u prime y1. Okay, and then take other derivatives. This will be u. Let me just write the result. This is similar from what we have before. Okay. Now substitute to the dE. So u, or let me write y double prime plus py prime plus qy. So this will be u okay, so let me write, this becomes y double prime is u y1 double prime is y1 double prime plus p y prime plus key y1, sorry, y1 plus y1 u double prime, this one, and then plus 2 y1 prime plus py1, okay, py1, and then u prime. This is for this one, okay? And this will be equal to 0. And this part here is 0. So we must have that y1 u double prime plus the whole thing here plus by1 u prime, this is equal to 0. Or we take the let w is u prime, and we can convert this and reduce the order. That's the idea, reductions. Okay, so we take this substitution, we take this substitution to reduce the order. Okay, so this becomes w prime plus 2y1 prime plus by1, and then u prime becomes w equal to 0. Now this becomes we can separate this. Okay, we can separate this. Let's say the w prime is with the x like that. So let's just multiply with the x. Okay. And then divide by w, so dx over w. Okay, so we are going to separate. Okay, we are going to separate. So dy and also y1. Okay, let me also divide with that. So dw over w, okay, plus 2 y1 prime divided by y1 dx, okay, and plus py1 w is cancelling, so p dx equal to 0. Okay, let me go through copying this. Okay. Okay, and then integrate, or let me write we integrate with respect to the x, so this is also integrate. I think this is w. Okay. Now this will be ln w plus ln y1, right? And the 2 becomes squared here, and then equal negative p dx. And let me just write plus c from the constant from the left. Now we can combine this w, y1 squared, okay, like that, combine, and then equal, or we can take the logarithmic, we remove that, and this will be supposed to be e with power of negative p dx plus c, but it's another constant, so let me just write with another constant to differentiate this. So let's say this is c1. And it's still in terms of w, so we need to go back to make it u prime, right? So this will be u prime y1 squared c1 e, or in our case here, what u prime is c1 e divided by y1 squared, okay? And then integrate okay, with respect to dx. So u prime becomes u equal, let me write constant outside of integrations, and this will be e negative p dx, and this will be y1 squared. It's dx and another constant on the right side. So we choose, okay, choosing c1 is 1 and c2 is 0. Okay. It's actually, we want to just remove the constant and to make sure that we get what we want. That is the second solution here, right? And we find that y is ux y1 x, right? So y2 is y1x multiplied with the integrations, dx. Okay. Okay, that's how we get the approaching, how we approaching the second solution. Okay, let me give you just remarks, like the example how to use this um, y2. Okay. So we can use this y2 if we are sure that we know the y1 is y1 is known from the given dE. Okay, and we can just using this integration with integrating factor inside. Okay. Okay, let me give you time for writing this. I think this is important. Maybe the last part. Okay. let's say we have y1 equal x squared is a solution of x squared y double prime minus 3x y prime plus 4y equals 0. The question is find general solution on interval 0 to infinity. Okay, this is one example that probably a typical question for this method. Okay. So the first thing is looking at this differential equation. Okay. Look this one. The first thing is we need to rewrite this form and make it into our standard form. Okay. So make standard form. That's the first step. So we divide by x squared. So y double prime minus 3y prime over x, right? X squared divided by x squared plus 4 over x squared y. So we have this 3 over x y prime, or let me write separately to make it clear. Okay. Now we find from this formula, we could directly write down this y2. This y1 is x squared, and then integrations, and then x with power of 4, and then e negative. The p is negative 3, so it's become positive. So positive, positive, it's become 3 dx over x, 3 over x dx. Okay. Now this becomes remember that this is still inside. So e 3 over x is our ln x, 3 ln x, right? This becomes 3 ln x, and this becomes ln x cubed. Or we can say that this is x cubed, and still it has dx. So we need to integral twice, okay? And then we need to integral one more. So this is 1 over x. This will be x squared ln x. Okay. So general solution is given by y equal c1 y1 plus c2 y2. So y c1 x squared plus c2 x squared ln x. This is the general solution. Okay. Okay, that's the reduction order. And I think I will just stop here because the next one is, I do think we need to have break before the next one because it's another method that you need to be think carefully. But before we end, I would like to give you some feedback, and you need also to give me another feedback, okay? Especially from your homework and maybe today's lecture from the morning and this afternoon. I believe there is really a slight gap or maybe a huge gap between the first order and then the higher order, right? Okay. Okay. Let me just go to my slides here. Okay. I would like to know whether you're still there. Okay, let me just give you some short question, and maybe you can also give me an idea, feedbacks, maybe some requests like from the homework that you're working on. Is there any specific questions that you're still missing some understanding on some subjects? Because in the higher order one, the subject becomes, for me, it's more becoming more abstract. Okay? Unless if we try to take some examples, it will be a little bit abstract if you lose focus on the first order differential equation. Okay. 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 Please join the comprehension 2. I will consider all the participation. Your participation is also activity. Okay. So let's start. Okay, 8 students. Okay, at least 9. Okay, 9, at least half. Okay, I think it's okay. Okay, let's start. Countdown. I'm not sure the time whether it's enough or not. I think it's too short, right? But just try. Just try. When you see the questions, you need to be able to distinguish whether this is linear, separable. Okay. Yeah, I think it's too short, right? It's too short the time. Forgot to change the time. Okay, time's up. Sorry if this too short. Okay. Okay. Uh, I believe most of you are just try your best. Like the if you can change your name, but I think that will be better. Okay, I can mark your grade into this student activity. Okay. Okay. Next slide. Okay, so is it true or false? Okay, it's supposed to be false. Okay. I hope you still remember how to find the exactness of the equation. Okay, the one who are Simba, you can change your name to student ID. Okay. I think last one. Okay, we have this equations. What will be the value of k? Yeah, I think you need to do some partial derivative. Some partial derivative. Hope you still remember that. Hope you still remember. Okay, a little bit more. Okay, thumbs up. Yeah, it's 10. Okay, 10. Okay. Okay, the one who gets 40, you need to equaling both sides. Divide by 4 is 10. Okay. Let's see who will be the winner. Okay. Okay. Congratulations. Okay. Congratulations. Before we end the lecture, okay, let me have your feedbacks if you have any feedbacks. Okay. And if you are not having any feedback or comments, just write your student ID. Okay. I think homework is okay, right? It's not too difficult. I think some of you just uh, forget some techniques in calculus. Okay, so you can review your calculus part. Okay. Okay, if there is no question or comments, then I will I will end the lecture. Okay, and thank you all for today's lecture. And I hope you don't mind if I just end the lecture now because the next part, yeah, a bit too much. Yeah. Uh, So for today's the higher order, yeah, I just lay some groundwork for the introductions part. Okay. The next sessions it will be more practical and we will be more having more some exercise and we will skip some parts so not all will be tackled in our summer course. Okay. So okay, I think that's all for today. So thank you for joining and see you on Wednesday. Okay. Oh, okay. The time for homework, right? Okay, okay. I will think about that. Okay. Okay. Thank you. Thank you for your feedback.